Welcome back. Welcome to part two of Plate Tectonics. In the previous part one of Plate Tectonics, we talked about continental drift and Alfred Wegener's contribution to continental drift with respect to the three lines of evidence, such as fossil evidence, climate evidence, and lithologic rock evidence, which Alfred Wegener introduced to the Science Symposium back in the 1920s, and it received hostile type criticism for his continental drift theory. And then later through the years, scientists were able to discover how active the ocean floor is with earthquakes and volcanic eruptions. And from there, the discovery of paleomagnetism, which records the movement of the ocean floor through magnetic reversals. And by the late 1960s, plate tectonics now is widely accepted by most, if not all, the geologists that I know anyway. So we're going to continue with part two of plate tectonics, and we're going to start looking at plate tectonics as a theory, the mechanics of plate tectonics. We'll look at various interactions along the plate boundaries and the various landforms that are formed. And then towards the end of the presentation, not necessarily part two of plate tectonics, but towards the end of the presentation, we'll discuss a little bit about what drives the plates and what theories or hypotheses are out there that allows the plates to move. So looking at this first slide for part two, we're looking at the plate tectonic theory. And again, on the onset of the late 1960s, plate tectonics explains a lot of geological occurrences. For example, the geographical location of mountains. Just to the east of us, we have the Sierra Nevada mountain range, which are granitic intrusive rocks. And one may ask, well, gee, if those are intrusive igneous rocks that formed below the Earth's surface, how did they get to the surface? And again, plate tectonics can answer that. Or how about why oil can be found in the Arctic? And today, as we watch, where oil typically would form is usually the tropical areas with lots of moisture and vegetation and lots of time. But yet, when we look at the Arctic, in the upper latitudes of the Earth, there's huge oil reservoirs. And so one might ask, how does oil get up to the Arctic? Again, plate tectonics can explain that, quite possibly. And it's been shown that the Arctic really sat along the equatorial zones of the Earth for about 400 million years. We mentioned earlier about the distinct pattern and occurrences of volcanoes and earthquakes around the globe. And yes, plate tectonics explains that because we find that most volcanic activity and earthquake activity occur along plate boundaries. And then we'll take a look at this one, the occurrence of the San Andreas Fault. And we know now that plate tectonics is directly responsible for the transform boundary that is produced the San Andreas Fault. So one can go down this list of various types of activities and landforms and so forth that exist. And again, it can be explained by plate tectonics. In fact, if you typically read a geologic report of an area, typically it'll always start off with some type of tectonic setting of the area. So at this point, by the late 1960s, plate tectonics really is coined as the universal theory. So let's take a look then at just a model that represents plate tectonics. And this is just a simple introduction model that really shows that the Earth's surface is composed of these solid, rigid lithospheric plates. They're very thin. We pointed out numerous examples on how thin the lithosphere is by giving an analogy of a hard-boiled egg, and typically the lithosphere is about the thickness of the shell of the hard-boiled egg. We can take the lithosphere and we can divide it into two components, and that would be continental and ocean floor material and the upper mantle. So the lithosphere is upper mantle, continental, and ocean floor material. And if you look down at the diagram where my arrow is, I have circled here the upper mantle, continental crust material, and the ocean floor. And also to drive the plates, or to allow the plates to move, the plates move along the asthenosphere which represents hot mantle rock. I kind of look at the asthenosphere as like hot wax. And so if you heat up wax, it gets kind of gooey, and these lithospheric rigid plates are allowed to move around and slide around the asthenosphere. And so that's the relatively simple model of plate tectonics, and we're going to expand with this model by looking at different plate boundaries and interactions along that plate boundary. So the Earth is divided into a series of segmented rigid lithospheric plates. And it'd be kind of analogous to going back to the hard-boiled egg. If you take the egg and you take this egg and you begin to pound the egg on the table lightly, and you'll notice that the shell will break up into these segmented shell segments or shell fractures. And that's really similar to what the Earth's lithosphere looks like. And so it's basically composed of these lithospheric rigid plates. There's about 30 plates altogether. And we can take those 30 plates and we can divide them into 7 larger plates. So there are 7 major lithologic plates that are recognized. And we have the North American plate, South American plate, the Pacific plate, which represents the largest plate, the African plate, Eurasian, Australian, and Arctic plate. And on average, these plates move about 2 inches per year, about 5 centimeters per year. And these plates will have a tendency to slide past one another, tendency to collide with one another, and tendency to separate from one another. And all these plates are jockeying for position, and along their plate boundaries, various landforms then are formed. So I like this picture here because it kind of gives you an idea the role of the continents in relationship to the plate. And in fact, the continents are not the plate material, but in fact, the continents ride along the plate material. So we really want to say that the continents go along for the ride. And so here you see this nice big piece of steak right here, which could represent Africa, for example. And then Africa is riding on the plate itself. This slide here shows the Earth minus the oceans. So we have to kind of look at this slide carefully, and it shows the current configurations of the continents. And you have to kind of look at it carefully because of the lack of water. And so what I like to do is find North America first. And so if we find North America first, North America lies where my arrow is. And you can kind of see then that Bakersfield would probably sit something about in that location. And you can see that the United States rides on the North American plate. And we come over here, and here's the Eurasian plate. Here we see Africa riding on the African plate. And then we can come over here, and we see the actual Pacific plate. And remember earlier we said the Pacific plate represents the largest segmented plate on the Earth's crust. And when you look at this slide, first you might say, wow, it doesn't look very big. In fact, you might say that the North American plate up here and the Antarctic plate located down here look quite a bit bigger than the Pacific plate. And really what you're looking at is an optical illusion, because you're looking at a flat map projection as opposed to this projection being on a sphere, in which is what the Earth is. The Earth is, of course, a sphere. So if I were to take this map projection, this flat map projection, and put it on a sphere, you would clearly find then that the Pacific plate would in fact be the largest plate. In fact, on the flat map view, areas near the equator along here are going to be the smallest. And as you move north and south of the equator, those areas get larger and larger on the map view. So certainly on a spherical view, the Pacific plate would be much larger. So when we look at plate boundaries, plates move relative to one another. All the major interactions along the plate boundaries create various deformation, which creates specific types of landforms. As we mentioned several times now, that along the plate boundary is where most volcanic and earthquake activity occurs. Now, there are 3 distinct types of plate boundaries. There's actually 4 types. We're going to cover 3 types in this discussion. We're going to cover the divergent boundary, where plates move away from each other. We're going to cover the convergent boundary, where plates move towards each other. And we'll look at the transform boundary, where plates slide past each other. And there actually is a fourth boundary known as the intra-plate boundary. And this is where we have what we call a hot spot or magma that is pushing up through the lithosphere, and the magma chamber or the magma itself is stationary. It does not move. And typically the plate will ride over the top of the hot spot. And so as the plate rides over the top of the hot spot, it'll produce a volcano, for example. Then the plate will move over the stationary hot spot, and another volcano will be produced. The plate will move again over the stationary hotspot, producing another volcano. And this really ends up producing a little chain of volcanic islands. And so the typical example of an intra-plate boundary or hotspot would be the Hawaiian Islands. This is a great slide showing the current configuration of the continents. You can certainly see Africa here, South America here, Asia over here, and unfortunately the United States has been kind of cut off a little bit. But this is a slide, again, with the absence of the water on the ocean floor, but it gives you an idea on how active your Earth is. For example, here's the mid-Atlantic ridge, and you can certainly see that this represents a divergent boundary where the plates are moving apart. Here is a great convergent boundary where we have an ocean plate colliding with a continental plate. Over here would be another divergent boundary, and this is where the Red Sea exists. And here you have the eastern part of Africa being moved away from Saudi Arabia. And then over here would be another convergent boundary where we have a continent plate colliding with another continent plate, producing the Himalaya mountain range right in here. And then what we're going to find out later about transform faults is about 95% of them exist on the ocean floor. And so as we progress through the discussion, I'll be showing you some diagrams and pictures of transform boundaries all along the ocean floor. So let's talk about the divergent boundary. And when we look at the divergent boundary, we're going to use the same animated slide that we use to describe a spreading ridge or spreading center. And that's because a divergent boundary is the same thing as a spreading ridge. And so when we look at a divergent boundary, we look at these interconnected oceanic ridges that exceed about 43,000 miles of length that kind of circumvent and wind their way around the ocean floor. And these have volcanoes and mountains, with some mountains being 2 to 3 kilometers higher than the ocean floor. So these oceanic divergent boundary ridges are pretty impressive. And you might want to think about the ocean or the arrangement of these divergent boundaries as kind of looking at a baseball. And if you look at a baseball and you look at the stitching that makes up the baseball, you kind of see the stitching of the baseball kind of wind its way around the surface of the baseball. And that's really kind of analogous to how you would look at a series of these divergent boundaries in the way that they wind around the ocean floor and wind around the surface of the Earth. In terms of activity, again, divergent boundary is the same as a sea floor spreading. So you would expect along the divergent boundary to have new ocean floor created at about 2 to 3 centimeters per year. One area just off the coast of South America, known as the East Pacific Rise, moves about 16 centimeters per year, which is about 6 inches per year, which is actually pretty fast for plate movement. In fact, at least once or twice a year, the west coast of South America will experience some pretty heavy-duty, high-magnitude earthquakes as a result of this fast-moving 16 centimeter per year plate. And as we learned with seafloor spreading, material grows equally on either side of the ridge. So here's our ridge. Material grows on this side and this side equally. And certainly that's evidenced by the age of the ocean floor and certainly evidenced by the paleomagnetism process. Typically, thicker seafloor will form at oceanic ridges, thinner seafloor towards the continents. That's directly related to the cooling of the extrusive rocks that are being extruded onto the ocean floor. For example, up at the ridge area, we would find that the ocean floor would be a lot thicker because the rocks are a lot younger and the rocks have just been extruded, the lava, and the rocks are newer. But then as we move away from the ridge, the rocks begin to cool. They cool over time. And then when we look at rocks cooling, rocks will have a tendency to contract and shrink. And therefore, as we move away from the ridges, the ocean floor gets a little bit thinner and thinner. And typically, when we look at the distribution of divergent boundaries, we find that divergent boundaries and spreading centers are located typically in between the oceanic ridges, in between the different kinds of plates, and sometimes very common in between continents. This example here shows a very simple diagrammatic view of a divergent boundary and what happens to the divergent boundary on the other end. Because so far we've been talking about a divergent boundary producing new rock material on both sides of the ridge, and that the divergent boundary acts as a conveyor belt of movement, but then we have to ask what happens on the other end. So I like this diagram because right here you can clearly see the divergent boundary where, again, the plates are both moving away from one another, but then also what's happening on the other side of the divergent boundary. And so if you look on this diagram, on the other side of the boundary, you see that we're entering a convergence zone, in which, in this case, the oceanic crust is being forced underneath the continental material. Later on, we'll have a very important term that describes material that's moving or diving beneath a continent in this case, or other material. And so the question is, we asked earlier, why is the ocean floor so much younger than continental material? In fact, we indicated in part one of plate tectonics that the ocean floor is, at least the oldest rocks on the floor are dated at about 165 million years. And yet the oldest rocks on continents are dated at about 4.6 billion years old. So there's quite an age discrepancy. Well, plate tectonics does a wonderful job in terms of explaining that age discrepancy between the continents and the ocean floor material. And if we go back to the diagram, we can see that as new material, new ocean floor material is being created at the divergent boundary, and then we come to the very end of the ocean crust, we can see that it's being consumed on the other side through a convergent boundary. And so this would really represent the very young rocks, progressively gets older, and then the very oldest part of the ocean floor you're not going to see anymore because it's being consumed in a convergent boundary. So this little segment between this point of the ocean floor and that point of the ocean floor really only is about 165 million years old. The rest of the ocean floor has been consumed and assimilated into the upper mantle. And so again, plate tectonics does a pretty good job in figuring out, if you will, why the ocean floor is so much younger than the continental material. Here is a slide, again, showing the current present configuration of the continents. And throughout the discussion that we look at and of interaction between the different types of plate boundaries, I'm going to give you geographical locations that look at the type of landform that formed as a result of that interaction. So for divergent boundaries, we are going to use the Mid-Atlantic Ridge. That's classic, because if you look at the Mid-Atlantic Ridge, you can see where it winds its way down through the Atlantic Ocean. And as it makes its way down through the Atlantic Ocean, you can certainly see that it lies pretty close to very smack in the middle of both South America and Africa. And it kind of matches that analogy of stitching on a baseball. And now there are other divergent boundaries. Sure, there's a divergent boundary down here. Here's a nice divergent boundary right here that's actually pushing India up into the Eurasian plate, and divergent boundary here, and so forth. But for our purposes in this class, our geographical setting will be the Mid-Atlantic Ridge for the classic divergent boundary. Now, the next question to be asked, can a divergent boundary, or makes new ocean material on the ocean floor, but can we also split apart a continent itself through divergence? And the answer to that is absolutely. In fact, there is places today on Earth in which continents are splitting apart. And I will give you an example of that in the next couple of slides. But let's go ahead and take a look at how a continent splits apart. And first, before we do that, we have to apply a term that relates to the splitting apart of a continent. So we used the word divergence, and we mainly use that for ocean floor material. And for continents, we're going to use the term rift. And so we would say a rift valley, or we would say continental rifting. And rifting means basically splitting the continent apart. So in this first diagram at the very top of your slide, we can begin to rift a continent apart by magma coming in contact with rigid lithospheric material. The magma is more buoyant, less dense. It wants to rise. As it comes in contact with the continent, begins to break it apart, and the continent begins to buckle and form cracks and little separation up at the surface. And I kind of like to look at this as analogous to a fig Newton cookie, for example. And so the fig would represent the asthenosphere, and the crust of the cookie would represent the lithosphere. And so most geologists agree that the magma finds weak spots in the lithosphere, and that's usually typically where the magma is going to start rising and breaking up the top of the lithosphere. If we allow continued rifting, and so the magma continues to rift and break apart and break through continental material, the crust will begin to pull apart, and it'll begin to experience tensional stresses, meaning that the crust is being pulled apart, separated from one another, and we start to create what we call a rift valley. And so a rift valley basically is a depression that forms in the crust. And it's also marked by these little blocks, and we call these fault blocks. We call these normal fault blocks. And these little blocks slip down from one another, and it forms these little structures on both sides of the rift valley. So further spreading, further rifting, if we go down to this diagram, and now the rift valley is widened. It's widened to the point where water can enter into the valley, the basin, and sometimes it comes in the form of a lake or a smaller ocean, and starts to cover up the little fault blocks, and the fault blocks now form continental shelf material. So right down here would be the normal fault blocks now being submerged under the water. If we allow more continued spreading, and so we allow it for over geologic time, so millions of years in this case, then the ridge, of course, will expand, get wider, more mature. You start creating an extensive amount of ridge material right in the middle here, and then the rift valley opens, and now in this case we can certainly put an entire ocean in the rift valley. In fact, this pretty much looks like South America and Africa. In fact, could this not be South America here, and then over here this being Africa? And if we jump up to the very top part of your diagram, could this not be Pangaea 250 million years ago? And so this, in terms of Pangaea, would break up in a similar process outlined in this diagram. And in fact, couldn't we have Mesosauruses over here, Mesosauruses over here, during the reign of the Mesosaurus? And then as the continent broke apart, it left Mesosaurus on both sides of the landmass. Hence, Mesosaurus fossils here and Mesosaurus fossils here. Now, is there a place on Earth today in which continental rifting is actually taking place? And we can go to this slide and look at the eastern part of Africa. And in the eastern part of Africa, we see various stages of continental rifting. For example, we have the Red Sea, or the North America, or where Saudi Arabia is separating from the eastern part of Africa, and now it's at a point or a stage of rifting in which the ocean is coming in. Here is a younger stages of rifting. Here we have a series of rift valleys in which the water has not quite been able to get in there. And then here is probably a little bit more of a late stage rifting valleys. You see some lakes in here. So this whole area of the eastern part of Africa is slowly under continental rifting. And if we could stick around for another 5 million years or so, we may see this eastern part of Africa detach itself and move away from Africa. Here is the other satellite example of the East Africa Rift Valley. And here again, you can see the previous slide up here where you see the eastern part of Africa beginning to slip away. Here's the satellite image, and I've drawn a line connecting the rift valleys. And you can actually get an idea of this part of the valley being rifted apart, broken apart, and split away. And if you were to walk along this area right in here as a field study, you would certainly see tensional forces at work by looking at the series of normal fault blocking taking place on both sides of the Rift Valley. So again, this is another example of a very active Earth.